scientists have their own special language, and I'm going to share one of the secrets with you now, how we write down really, really, really big numbers. It's a shorthand notation that includes all of the information, but it saves a lot of paper. And that technique is called writing a number in scientific notation. So here's a number that some of you may recognize already, and if you don't recognize it, it's no big deal, but it is a very big number. It's 602,213,700 followed by 15 more zeros. And obviously, if every time you had to write down this number, and for reasons that'll become clear, it'll be important to write down this number several times in your study of chemistry, you'd use a lot of paper. So rather than write it this way, what we're going to do is we're going to forget about all the zeros, not forget about them, but we're going to use a shorthand notation for taking care of all of the zeros. And the reason why we can do this is because the zeros aren't really significant numbers anyway. They're placeholders. And so what we do is we express numbers, either very large numbers or very small numbers, and both positive and negative numbers, by writing them in two pieces. And the first piece is a piece that includes all of the non-zero digits and maybe some zeros that happen to be interspersed in there. This is a number, this part of the number is going to be greater than or equal to 1 and less than 10. So in other words, there'll be a number followed by a decimal point, followed by a bunch more numbers. It's possible that you wouldn't have the decimal point, that it would just be a single digit, but the point is that digit is going to be 1 through 9. And then we have a multiplication sign, and then we follow by 10 to some power, where this power tells us how many zeros we have to include in order to get this number to be exactly the same as this number. And the way to remember whether this number should be positive or negative is, first of all, big numbers have a positive exponent, and small numbers, numbers that are less than 1, have a small exponent, a negative exponent. And to go from this number to this number, recognize that we go from this point, so there's an implied decimal point at the end of the zeros here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. In order to get the decimal point between the 6 and the 0, we have to move the decimal point 23 times to the left. And this 23 tells us that's how many places we had to move it in order to get it into what we call exponential notation. Now, one of the really good benefits of exponential notation is that every digit in this part of the number is a significant figure. So you have to consider every single digit here as significant. Now let's look at some numbers and convert them into scientific notation and make sure that we understand how we go about the process of getting from a number that's just written out with all the zeros to a number that's in scientific or exponential notation. 25.0, remember we want a number that's between 1 and 9.9999999, greater than or equal to 1 or less than 10. So to go from 25.0 to something in exponential notation, we have to move the decimal place one place to the left, which means that we put a 1 here, a positive 1, and that number is significant, so it's 2.50 times 10 to the 1. Here we have a number that's less than 1, and so we're going to have to move the decimal place the other way to get it into scientific notation. 1, 2, 3, 4. So it's 3.71, and then 10 to the minus 4, because we had to move the decimal place to the right to get it into scientific notation. And 1,376, again, we're moving it to the left. 1, 2, 3, so there's a 10 to the third. And here's 0.33167, so we'd have to move that one place to the right, and so we have a minus 1 here. Now, again, one of the great advantages of scientific notation is that the number of significant figures is unambiguous. So 100 is somewhat ambiguous, right? Does it have one significant figure? Does it have two significant figures? Does it have three significant figures? Some conventions say that if it has a period here, a decimal place, then it has three significant figures. And if it doesn't have a decimal place, then it only has one significant figure. And that's a reasonable way to do it, but it's somewhat ambiguous. It's entirely unambiguous if we express 100 in scientific notation, because we can either express it as 1 times 10 to the 2 power, which has one significant figure, or 1.0 times 10 to the 2, which has two significant figures, or 1.00 times 10 to the 2, which has three significant figures. If we wanted to express it to 4 or 5 or 6 significant figures, the point is we'd just be putting significant zeros after the decimal place, and the placeholder part, the 10 to the 2, goes along for the ride. Now, when we're doing arithmetic with numbers in scientific notation, if you're using your calculator, you really can ignore the rest of this lecture because your calculator is going to be doing what I'm telling you you could do longhand if you don't happen to have a calculator or if your teacher doesn't allow you to use calculators. We know, for instance, that 3.94 plus 0.67 is equal to 4.61. If this is written in scientific notation, it would be 3.41. So you don't typically write 10 to the 0 for numbers that are between 1 and 9.99999. You just would write 3.94 and forget about the fact that 10 to the 0 is just 1. And then if you're adding this number written in scientific notation would look like that. And what you have to do is you have to convert them both to have the same power of 10. So the exponentials must be the same when you want to add them. And so if we, for instance, converted this back into an exponent, put it in with an exponent of 0, it means that we would convert this number into this. So this number is equal to this number, 0.67 times 10 to the 0, just as this is 3.94 times 10 to the 0. So we can convert this number to here, and then we can get to the answer. And remember that when you're considering the number of significant figures in an addition problem, it is if we have 2 figures past the decimal point in this number and 2 in this number, then the product is going, then the sum is going to have 2 significant figures past the decimal point. Whichever number has the fewer number of places past the decimal point, that's what determines the number of significant figures in a sum or a difference. The other way to do this is to convert them both into numbers that have an exponent of -1. And of course, this number is not in scientific notation. But now that they both have an exponent of -1, we can add these two parts, and we get 46.1 times 10 to the -1. So when the exponents are the same, then it comes along for the ride. And then converting that back into scientific notation, we get to the same answer, 4.61. When we're multiplying numbers, recognize that 10 to the a times 10 to the b is equal to 10 to the a plus b, where this is the exponent. So 3.94 times 10 to the 2 times 6.7 times 10 to the -3, we don't have to do this conversion into a common exponential, but we do have to group together the part that isn't a power of 10. So for instance, we group 3.94 and 6.7, and then we group the parts that are a power of 10 and use the fact that 10 to the a times 10 to the b is equal to 10 to the a plus b. So we would add the exponents 2 and -3, and then we would multiply these parts out. 3.94 times 6.7, which if you work it out on a calculator, looks like 26.398. Then you have to put this part into the correct number of significant figures, which in this case is going to be 2, because there are 3 significant figures in 3.94, but only 2 in 6.7. So to the correct number of significant figures, this product is 26 times 10 to the -1 power. And then correcting it to scientific notation, we move the decimal place 1 place to the right, and that cancels out the -1 here. So the answer is 2.6. Plug it into your calculator, and you'll see that the answer is, in fact, 2.6 with a bunch of other numbers. But rounding, considering the number of significant figures, the answer is 2.6. Now, finally, we have to consider powers and roots. And once again, with powers and roots, if you're using your electronic calculator, it's not really an issue. But 10 to the a times b, 10 to the a power raised to the b power is 10 to the a times b. And so if we have a number that's r times 10 to the t power raised to the b power, so this whole number raised to the b power, it is r to the b power times 10 to the t times b power. And so, for instance, 6.7 times 10 to the -1 to the 4th power is 6.7 to the 4th power, and then 10 to the power t times b, which in this case is -1 times 4. Now, we multiply this part out again. This part is the part that has the significant figures, and I've expressed it with 4 significant figures here. So 6.7 to the 4th power, which is 6.7 times 6.7 times 6.7 times 6.7, is 2015 and a bunch of other digits. But this is already too many significant figures. When we round to the correct number of significant figures, which is 2, because we're multiplying, we get 2.0, and then 10 to the -4, we get back, this is 2015, so we get back 3 orders of magnitude, or 3 powers of 10. So those 3 powers of 10 cancel with most of the 4 powers of 10 here, so we get a -1. Let me express that. 2.015 times 10 to the 3 times 10 to the -4. So 2015 is 2.015 times 10 to the third, and then there's a 10 to the minus 4. So the 3 and the 4 from the previous page become a minus 1, and then when we round this to the correct number of significant figures, we get 2.0 times 10 to the minus 1. And to take square roots or nth roots, this is the bth root of the number r times 10 to the t power. It's r to the 1 over b power. Remember that a bth root is a number raised to the power 1 over b times t to the t over b. This is just an extension of what we had on the previous page. Another way to write this is r times 10 to the t power, all raised to the 1 over b power. And so that's r to the 1 over b times 10 to the t over b. And so if we were going to take the square root of 9.67 times 10 to the minus 4, it's 9.67 taken to the half power times 10 to the minus 4 raised to the half power. And that's 3.11 to the correct number of significant figures, and 10 to the minus 4 over 2, which is 10 to the minus 2. So again, all of the stuff about addition and multiplication, the only thing you really need to worry about is rounding to the correct number of significant figures. Your calculator is going to take care of the rest of it. But on the other hand, it would be great if what the calculator is doing was not a great mystery to you, that you were actually aware of the arithmetic and aware of the algebra and what exactly is going on. Other than that, scientific notation is a way to express really big numbers, numbers much, much larger than 1 or much, much smaller than 1, in a convenient way that makes it really crystal clear how big the number is without having to count all of the zeros.